um, recorded by the experimental. So I will give more details about my research work. And today, firstly, I will give some background and motivation because I'm not sure how many are familiar with the de-icing research. And the second part is about the research topics related to the aero-engine de-icing. Although there are 5 different research topics, but they are both related to the aero-engine de-icing. And the last part is a summary. So aero-engine de-icing is also a very serious hazard for the aerospace industry. So, and they always create the danger for the flight testing. And here is an animation. I want to show you how the aero-engine de-icings affect the work of the aero-engine. Let me, can I play this one? Okay, so let me try. I'll try to play this in. Okay, there we go. So when the aircraft flying on the air, there is a supercooled water droplet impinged with the rotating fan blade or the inlet guide vent, and there is an ice formation on this part. When the ice spread out from the blade, it will cause the aero-engine problem. For example, these ice accretions will cause the power loss of the aero-engine, like the stall, roll back, and flame out. And since 1988, there are more than 150 jet engine power loss events, and this mostly happened in the descent and cruise status. And here is one example for the British Airways 777 crash in 2008. There is ice block the inlet of the system, which will cause the crash of this aircraft. And for today's aero-engine de-icing hazards, there is more challenge for the engineers or the researchers, because the turbofan engine become larger and the aerodynamic shape, the spinner and the blade is more complex. And compared with the airframe icing, there's one significant factor is the rotation movement, which will cause the centrifugal force for the aero-engine icing process. And also, the aero-engine needs more robust and effective anti and de-icing technologies, because there's limited source for the anti and de-icing technology, and also the space for the aero-engine is more limited. And these are some pictures to demonstrate how the ice accumulate on this aero-engine parts. Basically, there are 2 aero-engine icing. In this research area, people divided the aero-engine icing to 2 parts. The one is caused by the supercooled water droplet icing. The other one is caused by the ice crystallizing. The supercooled water droplet icing is similar to the airframe icing. When the cold air with supercooled water droplet, freezing drizzles and freezing rain, and this mostly happen at the inlet of the aero-engine. For example, here the purple color shows how these ice accumulate at the inlet lips, the spinner, and the flame blade, and also the inlet guide vent. And the ice crystallizing is caused by the warm air with crystals or droplets. And this crystal will be melted inside of the ice, inside of the aero-engine. And they are mostly happen at a high pressure compressor and combustion chamber. And for the present research, I focus on the supercooled water droplet icing for the aero-engine. And just to clarify how this icing are divided. For the icing, basically, especially for the supercooled water droplet icing, there are also two typical types ice. The first one is rime ice, and the second one is glaze ice. The difference between them are depending on the temperature of the upcoming airflow and the liquid water content. So these two animations showed how the difference between the rime ice and the glaze ice. For the rime ice, the ice is rough, and for the surface is the milk colored. But for the glaze ice, is more complicated shape, and the ice accretion is faster than the rime ice, and also they will cause the water run back because the temperature of the oncoming airflow is relatively higher than the rime ice. And the glaze ice is the most dangerous types of ice because when the glaze ice accretes on the airframe or the aero-engine, it will significantly change the aerodynamic shape of this part, which will degrade the performance of the aero-engine. And these two types of icing shown here. Before I go to the details of my research topics, I want to introduce the unique research facility, the Iowa State University Icing Research Tunnel. And this research tunnel is the very multifunctional icing research tunnel. And the temperature varies from the -25 Celsius degree to the room temperature, and the flow speed can change from 5 to 100 meters per second. And these parameters allows the icing research tunnel to be run over a very wide range of conditions, like the dry rime ice and to the very wet glaze ice. And all the research of the present study were conducted in this research wind tunnel. All right. So, as I mentioned before, spinner is one exposure surface of the aero-engine. As we know, there are three major manufacturers of aero-engines. If you look at the pictures shown here, you know, there's Rolls-Royce, GE Aviation, and Pratt & Whitney are three major manufacturers of the aero-engines. The next time, if you take the aircraft, you can try to find out which company make the engine, because their springer's shape are obviously different for each other. For the Rolls-Royce, the springer is conical, and for the GE is a elliptical springer, and for the Pratt Whitney, they prefer to use elliptical springer. So for the first study, I want to examine how this springer's shape affect the dynamic ice accretion process and what the icing influence for the airframe and for the aerodynamic performance of the springer. And this is some design parameters, and the fan model is is the model for the Boeing 18-inch fan rig. It's a model developed by myself. So the next one, I show you how the experimental setup in the icing research tunnel. And this is the model, and it's rotating. So when it's rotate, the oncoming airflow with the supercooled water droplets impinge with this springer. So the right part show you how the ice accumulate on the springer when it's rotating. So for this animation, you can see the significant difference of the ice build-up process. For the conical, you can see there are the whole covering for the ice. But however, for the elliptical, there is only a small part at the tip have more ice. And for the conical, there is about half part has the ice accretion process. And that means these three kinds of springer shape have a significant effect for the ice accretion process. And I also used the digital imaging processing technology to digitize the rime ice accretion process for the springer. And in order to answer the question I pose up, why this aerodynamic shape affect the ice accretion process. So in order to answer this question, I do some tests by the PIV system. And for this test, I used the water droplets as the checking droplets. So here shows the water droplet trajectories for these three kinds of springers. For the conical one, we can find that the water droplets impinge for the whole surface from the tip to the root area. However, for the conical and elliptical, only a small part have the water droplets impingement, which means most of the water droplets will fly over the springer to impinge with the fan blade at the downstream. And this can help us to better understand why the ice build up different on these three kinds of springers. The next one, I try to use some parameters to define the impingement influence for these three kinds of springers. The first one is local impingement efficiency. And also we have a total impingement efficiency. For the right, the figures show for the connect code, the local impingement efficiency is very high at the tip area, and then goes down to the downstream. And for the total impingement efficiency, we can see that the conical have the largest one, which means the for conical spinner, it has more ice buildup on this surface. For the digital images processing, I can also estimate the accreted ice mass on this surface. We can find that the conical have the most iced accretions. So this can give us a more clear insight of the spinner's ice accretions. Is the impingement limit. For the impingement limit, we can find that the conical is close to 1, but for the elliptical and elliptical is relatively smaller than the conical one. And for the PIR test, the flow field measurement, we can find that when the ice build up on the fan blade, it will cause a flow field distortion near the spinner and the fan blade. And this will degrade the aerodynamic performance of the aero-engines. After I investigate the ice accretion process on the spinner, I want to deeper to investigate why the heat, how the heat transfer behave on this process. So for the second part is the unsteady heat transfer process over these 3 kinds of spinners. So it's the same setup, but the infrared camera is used to record this transition process and the temperature distribution on the spinning surface. So here's the simplified heat transfer model developed by the energy conversion model. And we can find that the temperature change, delta T, is highly related to the freezing ice mass on the surface, and also related to the heat convection and the heat conduction. And the 3 animations showed here is the first 20 seconds when the water impinge with the rotating spinner. This obviously demonstrates that the water and the ice affect the whole area of the conical spinner. But for the connectical and elliptical, the ice built up gradually because this green color means the temperature increased, but it's lower than the tip area. This means the water run back from the upstream to the downstream. If I distract the temperature difference various times, we can find that for the conical, the surface temperature change significantly to a very uniform distribution. However, for the conical and the elliptical, the temperature change gradually. When the times grows, the temperature increase gradually, which means we can find the water run back on these two kinds of spinner, and this can help us to better understand why there are ice accretions at the downstream of the elliptical and elliptical spinner. After that, I also used the high-speed camera to observe the details of the ice accretions here. So we can find that the feeder-like ice scones build up on the ice surface, as you see on the animations before. And if I observe the temperature change figure, I can find that for the initial time, there is ice surface buildup on the spinner's surface. However, there is strong latent heat of fusion, which will increase the surface temperature. When the incoming flow with water impinge, they cannot be frozen immediately, and which will cause the water run back on the surface. And that's why there is ice feeder-like ice circles built up at the downstream area, and which means the water run back contribute for this ice circles buildup. After I investigate the spinner icing, I want to know more icing problems for the whole fan. So the fan is very large, as I mentioned. For the GE90, the diameter is about 3.3 meters. But for the very old version, like CFM56, there's only 1.5 meters. So even the dark reduce loss in thrust and the noise. However, the ice buildup on the blades will block the air passage and decrease the fan's efficiency. And the ice shedding from this blade will destroy the components inside the engine. So here is the picture to show how the rotor blade damaged by the ice debris. If this happened, it will be very dangerous for the aero-engine safety. It will be sucked inside to cause the power loss events, as I mentioned. So for these research topics, I want to investigate how the ice accrete over the aero-engine fan blades and how the ice affect the performance of the fan unit. It's different from the previous model. A duct was added with the fan model to simulate the real aero-engine flow inside. And I also used the pressure change to estimate the thrust change for the aero-engine. And also the input power was also used to measure how the ice buildup for the aero-fan will cause the power loss for the fan. And in order to investigate how the ice affect the fan blade and the aero-engine fan performance, the temperature is changed from -5 Celsius degrees to -15 Celsius degrees. And the liquid water content is also varies from 0.5 to 2. And these matches will cover the rime ice condition to the great ice condition. Now, also the rotation speed is a constant during the icing process. And the mass of water sprayed into the icing research node is a constant. So that's why the icing time is different for the different liquid water content. In order to compare the influence for the icing conditions. And here's the animation to show when the liquid water content is fixed, but the temperature varies from the relatively higher to lower temperature to see how the ice build up on the aero-engine vent unit. For the first one, you can find that there is an ice circles build up on the spinner, which is related to the previous research studied on the seminar. And also, for the fan blade leading edge, the ice buildup is flat and is clear. This is typical glaze ice accretions. When the temperatures grows lower, the ice condition change to the rime ice condition. For this one, we cannot find the feeders like ice circles build up on the surface, but we can see there is a very thick ice accrete on the leading edge of the aero-engine fan blade. If we change the liquid water content to the 0.5 gram per cubic meters, but also varies the temperature from -5 Celsius degrees to -15 Celsius degrees. Most of this condition are close to the rime ice condition. They have a similar phenomenon for the ice build-up process. The next one is change of the liquid water content. The temperature was fixed at -10 Celsius degrees C, and the liquid water content varies from 0.5 to 2.0 grams per cubic meters. And this icing buildup changed from the rime ice to the glaze ice. For the 2.0 grams per cubic meters, there has water run back. You can see here, there's water run back on the surface, and smaller ice circles build up at the downstream area. After the icing test, we take the pictures for all the blade ice build up here. You can see the significant difference between the liquid water content and the temperatures influence. For the right corner here is close to the glaze ice condition, but for the left corner here is typical rime ice. And the middle, people always call that the mixed ice. It's between the glaze ice and the rime ice. And after we compare the ice features for the glaze ice buildup, we can find that this is the ice accretion over the fan with the dark. We cannot find the ice buildup at the blade tip. However, if there is no fan duct for the fan blade, the ice buildup on the fan blade will extend further from the surface. And for the rime ice condition, there is a very interesting phenomenon is the leading edge highs on here. And at first, I don't know why there is ice hole built up on the leading edge of the fan blade. But after I compare with the PIV test result, we can find that the water trajectory have a very water contractions here. There is a high water connection area close to the downstream area of the spinner. That means at this local area, there is more water impingement with the blade, and that will cause the ice home buildup at this wood area. If we compare the pressure difference coefficient of the fan blade, we can find that for the icing process, the pressure difference coefficients decreased significantly, especially for the glaze ice condition. But for the rime ice, the change of the pressure difference coefficient is not obvious. Even the pressure difference coefficient increased gradually. This is because the rime ice buildup on the fan blade increased the fan blade area at this time, which means it will cause more thrust by the fan with ice accretions. Because the ice for the rime ice, the surface is smooth and the area become larger. That's why the pressure difference coefficients increase a little bit for the rime ice condition. For the input power rotation, we can find that for the all icing conditions, the input power increased significantly. As I mentioned, the rotation speed is a constant. That means in order to maintain the rotation speed under the icing accretions, we need more powered input to drive the motor to keep the constant speed. And we can find that the power input increased about 10 to 20% for the rime ice condition. But for the glaze ice condition, the power demanding is over about 50%. And this is very, it's very dangerous for the aero-engine because there's no extra power for the aero-engine to drive the fan blade, the fan under the icing condition if the ice cannot be mitigated from the aero-engine fan. So in order to anti or de-icing, the next part, I want to introduce bio-inspired technology. I know maybe some of you are very familiar with this lotus effect. And this is a super hydrophobic coating, which already widely applied in the daily life and the industry. So for the anti and de-icing technology, we have passive and active methods. And this bio-inspired coating is one kind of the passive method for the anti-icing technology. Because for the aero-engine fan blade is rotating, and I guess the rotation effect could enhance the efficiency of the anti-icing performance of this coating. Before we apply this coating for the aero-engine fan model, I test the force capillarity, the capillary force for this surface. We can find that the uncoated hydrophilic surface, the contact angle is very small. But for the lotus leaf-inspired super hydrophobic coating, the contact angle is relatively larger. So we use the hydrophilic surface as the baseline, and the super hydrophobic coating the compare it with the baseline. So this is the animation to show these two kinds of coding applied for the frame unit model. For the animation, we can find that under the same icing condition, the superhydrophobic coating has less ice buildup on the surface compared with the hydrophilic surface. And this is a very inspired result, because for the aero-engine fan blade, we cannot apply the heating or the breathing air, because the blade is very small and there is no it's not easy to use the breathing air to heat the blade surface. But for the coating is more effective, and also is economy matters. When we apply this super hydrophobic coating, you can find that the ice accretion is significantly less than the hydrophilic surface. And these three pictures show you how the ice build up for these two kinds of coating surface. And also, we compare the pressure difference and the input power for the friend model. We can see if we have the super hydrophobic coating, the loss of the pressure difference is tiny. It's about 33%. But for the hydrophilic, the pressure difference is very large. And for the input power, you can find that the super hydrophobic coating unit, the power input only increased about 16%, which is relatively smaller than the hydrophilic surface. However, we cannot to maintain this effect, because when the super hydrophobic coating change from the tensile backstone statics to the Vansel statics, the tiny structure of the surface cannot work anymore, which means at the very first beginning, the super hydrophobic coating works, but after a long time exposure to the icing condition, the efficiency becomes very small, and it cannot to prevent the ice accretions on this surface. So these are the tests for the bio-inspired coating for the aero-engine fan blade anti-icing technology. The last part I want to introduce is the ice accretions for the inlet guide van. The inlet guide van is also one critical components of the aero-engine. There are various locations and the size you see at the inlet for the compressor. When the ice build up on the inlet guide van, it also blocks the air passage. As you know, the inlet guide van is easier to apply the anti-and de-icing system, because for the air engine, they can use the hot air to breathe, to blow the inlet guide vent. And for this research topic, I want to evaluate how the anti-icing and the de-icing performance of a hot air circulating system for the inlet guide vent system. So we developed an IGV model, and this is a profile for the NACA 012, and which represents the inlet guide vent for the aero-engine. And for the inside, there is a heating channel inside. The hot air is blown from the inlet, and the good air, after cooling, after heat exchange between the inlet guide vent, is blown out from the outlet. And the surface temperature were measured by the thermocouples and also by the high-speed camera to observe how the ice accrete on this surface during the anti-icing process. And this is an energy transfer process under the dry condition. So we treated this IGV as control balloon, and this is hot air in and hot air out, and only the convection played a significant role for this IGV. So the convective heat transfer is the biggest part for the energy lost during this process. And before we conduct the icing test, we find the heat flux under the different hot air mass flow rate for the surface. We can find that the heat flux at the leading edge area is the biggest one, and then the heat flux at the downstream becomes smaller. So the first we test the different hot air temperature for this hot air system, and we can find that for the typical glaze ice condition, if we change the temperature of the hot air, the anti-icing performance will change a little bit. When the temperature is lower, the water cannot be frozen at the impingement. However, when the water runs back, it will be frozen again at the downstream. And this is because the temperature at the downstream is much lower than the leading edge, and the temperature of the water become lower again. So that's why there is a small part for the ice buildup. You can see the surface temperature become lower than the 0 Celsius degree C. And for this slide, we show you if we change different hot air mass flow rate, there is also a significant change for the ice accretion process. Still for the same glaze ice condition, without the hot air, there is ice accretion on the leading edge, and the thickness become very large. When the hot air on, for the mass flow rate change to the largest one to the lowest one, the ice buildup at the downstream area become larger and larger. So here is the mass flow rate only is 2 grams per second, and there is over half area of the inlet guide vent has ice buildup, and this will also cause the aerodynamic performance loss for the inlet guide vent. And this is not, I mean, it's not good for the aero-engine's performance. So if we want to have a better performance of the inner the gyro, we want there is no ice buildup on the inner the gyro. This is also show the surface temperature drop from the larger than 0 Celsius degree to lower than 0 Celsius degree C. So here's a summary for this research topic. The first, I compared the spinner's geometric shape influence on the dynamic ice accretion and the unsteady heat transfer process for the 3 typical types of spinners. And also I provide more insight for the dynamic transition ice accretions for the rotating aero-engine fan blades. And the next one is I try to validate the feasibility of the super hydrophobic coating for the aero-engine ice mitigation on the rotating aero-engine fan. Now, the last part is for the bleed air system, we find that the mass flow rate and the temperature are two significant factors for the anti and de-icing strategies. So if we adjust these two factors, the aero-engine can find a more efficient operations condition in the cold weather. In the future, I want to better understand the influence of geometric shape for the anti and de-icing efficiency, and also the material property for the aero-engine icing is not investigated deeply. And also the de-icing performance of this bleeding air system is desirable as well. So thank you for your listening, and this is my presentation. Any questions?
Yeah, thanks Linkai for this like very encouraging presentation. I'm very surprised like during 3 years, like I mean I left the lab in 2016 and I suppose you graduated in 2019. So how much work you have done in these 3 years? You must be working hard. Yeah. Anyway,
thank you.
So we would like to take any questions from the audience. Like you can directly open your mic or you can leave your question in the chat.
Hello, I have a question, Linkai.
Can
you hear me?
Yes, yes.
Okay, yeah. I was wondering, is any technique that can measure the near wall air temperature instead of the wall temperature, so we can see how the flow, I mean the temperature transfer in the air?
Good. That's a good question. You mean you want to measure the air temperature, right?
Right.
Based on my knowledge, I know there is some. If you want to use the I know the Doctor Who has a molecule, the MTV, but I'm not sure whether it can be used for the air. Maybe you can we can find some papers to see whether we can measure the temperature on the air. The other one is you use the probe, like a temperature probe, to measure the air temperature.
Okay. Yeah. I think my question is mainly for the non contact measurement techniques. Maybe MTV is a way, but I'm not sure if it is working well in the air or instead of in the water. Yeah. Anyways, thanks for your talk. It's very interesting.
That's a very challenge. That's a challenge question.
Yeah. Okay. Thank you.
So I think like MTT works in the air, and I remember I look at some like Japanese people in JAX, they did some like it's not MTT but MTV use like I forget the material's name, but anyway, like they use that vapor as a like phosphorescent source, and then they like with a like high speed laser, you can always get a distortion. So as long as you can measure the velocity, I suppose if you can get the intensity like correct and you can like calibrate it, you might be able to do it as well in the air.
Okay, good. Thank you.
So any other questions?
Hello. Can you hear me?
Yes.
Yes.
Thank you very much for your perfect presentation. I have a question regarding to the infrared camera that you have used for calculating the temperature at the surface. I'm wondering if the existence of some ice layer on the surface is going to affect the result or not, or if there is any kind of other method to reduce this effect that you can suggest or not.
Sorry, I cannot hear very clearly. You mean the camera?
I mean, when you are using the infrared camera for measuring
the infrared camera?
The thermal camera that you just use for measuring the surface temperature.
Oh, yes.
I mean, if the existence of the ice is going to affect the results or not on the surface.
I use the infrared camera to measure the temperature of this surface. You mean what? You mean the brand? Or
Yep. I mean, when the surface is covered by the ice layer, is this thermal camera going to work well without any deflection or something? Because it's supposed to use for the surfaces which are not covered.
Yes. I use the back plane for the model to increase the emissivity and to make sure the ice emissivity and the water emissivity and also the background emissivity are the same, are very close to each other. I answer your question?
Not actually. If it's possible, you just explain it a little bit more.
Oh, so I'm sorry.
Yeah, essentially the camera's brand is FLIR, FLIR.
Yeah, the brand is FLIR. Yeah, the FLIR.
So that's
FLIR A600, FLIR 600, I think.
So regarding the surface, I'm not expert like using infrared camera, but like I'm pretty sure that's like you have ways to like make the ice surface, water surface, like temperature measures could be like quite precise. And actually, I don't think like the thermal surface for the ice and water is terribly different there.
Yeah, I mean, I know that this is not going to change the results so much, but I'm just looking for any other method to be like more precise or something. If you are aware of existing any other method or something, that would be great.
Yeah. Okay. Yeah. I what I know is now the infrared camera is one useful manner to measure this ice surface temperature. Yeah. But if you want to have more precise results, the thermocouples is desirable, like the surface.
Okay, thank you.
Yeah.
So, is there any other questions there? If not, I will ask the last question. So Linkai, I think it's on slide 29. You mentioned the Boxster to Winslow transition. for the super hydrophobic structure.
Yeah.
Could you share the slide?
Oh yeah, sure.
So essentially, I did remember like Rai did a test in the icing tunnel with different wind speed, and Rai thinks like it is droplets impinging on the tiny structures of the surface, which like is sort of like the velocity is high, so dynamic pressure is very high. So it's like instead of like it can flow on the sort of tiny structures, it's like the pressure will push the droplets go into the tiny structures, I mean the micro-sized structures, and then make it lost super hydrophobic. But like for your curve on the right lower corner, it seems like your power loss is increased gradually instead of like instantaneously. So did you also observe something like, say, like near the impinging, like sort of like it immediately lost the Cassie-Boxer state, and then like it's sort of like, I mean, is this process happens like the curve you showed, or like you notice something weird like during the test?
This is so if you see the red one, you can find the input power increased gradually, right?
Yes, yes.
And so for the ideal condition, there should no ice build up on this surface.
Yes.
Right.
Yes.
Because the water can be flow out, or maybe like the broke out for the blade surface. However, there is still input power for the airframe, which means there's also ice buildup. So for the animation here, even the ice accretion is much lower than the hydrophilic, but still have ice buildup on the leading edge area, right? Because for the leading edge, the dynamic pressure is the largest, and that's why it will change the surface status from the cassius to the Wenzel states, right? And
right,
that's why we find that the input power still increase, but it's increased. I mean, it takes more time. You see, it takes more time for the super hydrophobic coating, but when it become the same, is also the input power is the same as a hydrophilic, but it takes about like 80 seconds. But for the hydrophilic, it only takes about 20 seconds. So this is my hypothesis is even the super hydrophobic coating can work, but it cannot maintain the surface for a very long time exposure for the icing condition. We still need more robust or effective mixed ice, anti-ice or de-icing technology to make sure the aero-engine can run on a very safe condition. So can I answer your question?
Yes, sort of, yes. Yeah, essentially I remember like I did a test, even it's not published, like say we as a leading edge with summer strip provides like temperature to prevent ice, and then at the back side of the airfoil we use super hydrophobic. It was very good. So I think like if you want to improve like your test, you may can add one more compare case here, like in the leading edge, you may do something, and then at the backside you use super hydrophobic, or even in the leading edge you don't do anything, but at the backside you use super hydrophobic to see. Like,
yeah.
I mean, on the backside you shouldn't have like like the pressure push the surface. So it's all water just flow on the surface. So it should be like it should be like a good idea, maybe. I don't know.
Yeah, that's a good suggestion. Thank you.
Okay, yeah. Thanks, Linkai, for this excellent, like actually very impressive presentation. So thanks everyone for participating in the IBiM talk again, and we'll see you next week. That's all
Thank
for
you.
today. So Linkai, bye.
Bye. Thank you.
Thank you. Bye.
Thank you. Bye.